This is page 10 of the communication notes, and now we are going to look at M1K queues. So in other words, they have finite size, which is applicable to bounded buffers, which is kind of the whole point of bringing up queuing theory for this course. Because really the question we want to answer is, how big do the bounded buffers need to be so that we don't lose too many packets? So what we've got, again, as a reminder, here are clients arriving at the queue, entering the queue, and they're taken off and processed by the server. And so just a reminder that K is the number in the queue plus the one being served. So the probability of 0 clients in the system is P0 equals 1 minus rho, which is what it was before, but now this is divided by 1 minus rho to the k plus 1. So the denominator here is going to be less than 1, which means that the probability for 0 clients in the system is actually going to be bigger than it was for an unbounded or an infinite sized queue. And it kind of makes sense, because when you have a limited size queue, what's going to happen is once in a while a client's going to arrive and the queue is full and it can't be accepted, so it will be lost. So overall, your server is going to end up servicing fewer clients, and so the probability of having 0 clients in the system should be higher. The probability of n clients in the system is P sub n is equal to rho to the power of n times P0. So that's rho to the power of n times 1 minus rho all over 1 minus rho to the k plus 1. So again, this will be higher than the probability of having n clients when you have an infinite size buffer. And what's of interest to us is, what's the chances of losing clients, say their packets of data, and that's called the blocking probability. And this is the probability that a new client is blocked or rejected, and that's going to be equal to the probability of k clients in the system. So if you can only hold k clients in your system and a new one arrives, that one's going to be rejected. So the blocking probability is PB equals PN equals K, which is going to be equal to rho to the power of K times 1 minus rho over 1 minus rho to the k plus 1.